Lab 2 required me to observe an object moving with changing velocity. I analyzed the video of the object in motion using the computer software Tracker in order to obtain the initial conditions from the experimental model that were needed to create the computational model in VPython in order to predict the motion of the object. The objective of the lab was to show that the object's motion is consistent with Newton's second law by finding the relationship between the motion graphs yielded by the computational and experimental models. After doing so and comparing the graphs created with the data collected, it can be observed that the motion graphs for the computational and experimental models are very similar to each other. The computational model accounting for drag force predicted the motion of the object almost perfectly, while the computational model without drag force overestimated the velocity of the object compared to the experimental model. Here is the original video of me dropping the object from rest. I put this video into Tracker. I set up an axis with the origin located at the object's center of mass, and the object's motion moves in the negative y direction of the axis. I set up a calibration stick, which spans my height. I then tracked the object's motion using the tracking tool, indicated by the red diamonds. It can be observed that the object's velocity is not constant because it speeds up as it moves in the negative y direction, or closer to the ground. When relating this situation to Newton's second law, we can conclude that since the velocity is not constant, the net force is a non-zero number. After tracking the object's motion, I determined the initial conditions for the experimental model by looking at the data found in Tracker. The observed start time was 0 seconds. The initial position, 0.005 meters, was determined by looking at the first y position on the chart found in the bottom right corner. This is also where I determined the last observed time of the object's motion, which is 0.568 seconds. Its initial velocity is 0 meters per second because it started from rest. The object's mass is 0.05 kilograms. In addition to the initial conditions determined in Tracker, the computational model also requires the use of these concepts. Newton's second law is used to calculate the final velocity of the object, or ball.vel, found in the code under the comment, predict new velocity. The second equation seen here is used to calculate the final position, or ball.pos, found under the comment, predict new position. The third equation is used to incorporate the gravitational force into the code. The fourth equation shows how we calculate drag force, and the final equation shows how net force is equal to drag force combined with gravitational force. I used the Lab 2 start code in order to create my computational model, and modified it by inserting my initial conditions and changing some equations to reflect the concepts I just discussed. This is my Python code for the computational model that does account for drag force. I changed ball.m to reflect the mass of the object that I used in my original video. I used the initial conditions determined through Tracker in order to update ball.pos and ball.vel, the initial position and velocity. I left the initial time as t equals 0 since that was the observed experimental start time. I modified the drag constant b until the code yielded a final position within a few decimal points of the final experimental position, and these two positions did not match up until the drag constant was negative 0.011. As I discussed earlier, I included the gravitational and drag force equations in the code and calculated the net force by adding the gravitational and drag forces together. I used Newton's second law to calculate the final position and final velocity of the computational model. The computational model with drag produced an object that moved in the negative y direction and the position versus time graph that shows the increasing velocity of the object. This is my Python code for the computational model that does not account for drag force. This code only differs from the code with drag in one way. The drag constant b is set equal to 0 while the previous code had a non-zero number for b. The same modifications were made to the force equations and the initial position and velocity equations as were made in the computational model with drag. The computational model without drag also produced an object that moved in the negative y direction and a position versus time graph that shows the increasing velocity of the object. If the object were thrown downward, the terminal velocity would be the same as the terminal velocity of the object when it is just dropped. When the object is thrown, it reaches the terminal velocity quicker than when it is dropped. The computational model that accounts for drag force would predict a terminal velocity because such a velocity occurs when the drag force is equal to the gravitational force. This would happen in a model that includes drag force. As you can see on this graph, the computational model accounting for drag force predicts the motion of the object almost perfectly because its velocity, represented by the slope of the line on this graph, looks basically identical to the velocity of the experimental model calculated in Tracker. The computational model without drag force overestimates the velocity of the object compared to the experimental model since the final position of the computational model without drag is more negative, causing its velocity in the negative y direction to be greater than that of the experimental model.